Welcome to our sixth, actually it says fifth, that's a lie. It's our sixth learning workshop over solution, stoichiometry, and Net-Ionic equations. We will start with Net-Ionic equations and then go through how to use these types of equations and other equations to, along with the calculations of molarity, etc., in order to calculate various quantities in chemical reactions. And Dr. Nilafar will take us from here.
Okay, so let's go and write a balanced chemical reaction for the first question. And then in the second step, let's write a total ionic equation. And then in the third step, the Net-Ionic equation. So Ethan, I'm going to hand the baton to you.
Okay.
So let's see. Yes. What is the, yeah, if you would please first write the products and then let's go on balance.
Yeah, what
All
would
right.
you
Do you want me to do that on screen?
Well, well, first of all, like, what would you do to come up with the products here?
Well, so my first reaction is since they're both ionic, I think.
Yes.
I'm going to do double replacement, and so it's going to be some amount of potassium with some amount of phosphate. So it's going to be potassium phosphate and aluminum nitrate, and then I'll go back and balance them.
Yes.
Okay, so kind of, with these particular types of reactions, I might suggest first identifying the ions that are present for each of the compounds that you're starting with.
Okay.
So
I'm sorry?
So what's the charge on each of these ions?
Okay, so potassium is going to be positive. Phosphate is going to be a negative 2. Oh, it's -3.
-3.
Okay,
Yeah.
that makes sense. Shoot.
Unfortunately, you have to have this memorized.
Yeah, it's kind of. I found a mnemonic, by the way, to help remember them. It's pretty decent.
At first I thought you said it's kind of demonic, and I was like, well, you know.
Oh. Well, it
no.
kind of feels that way as well.
So what about aluminum? What about aluminum? What do we got for aluminum?
I'm sorry.
So that's gonna.
I was going to tell you a quick trick. If, for example, you forget what is the charge on this polyatomic ion phosphate, if you look to the subscript of potassium, you'll see that it is a 3. So you can cheat. You can say, remember the crisscross rule? You say, aha, I don't remember the charge, but K has gotten a 3, so it must be 3 minus.
I did not know that, and that makes sense as well. Huh.
You got to be careful. You got to be a little bit careful with that though, because that only works in the case if there's like it only works in a case where the number the charge of that ion is 1. So like if the charge of potassium is 1, then the number of potassium
Oh,
is
right.
with the charge of the other one. Or
and if it had been
yeah.
If it had been 2, you would have just divided the number, and that would have given you the
it would
same
have been
thing?
a -6. It would actually have been. So if like potassium was
Gotcha.
if the potassium was a +2, then the charge. So yeah, you effectively. Yeah, you get into a little bit of a mess there. Dr. Neely is not wrong. In most cases, it works. In fact, probably upwards of say 90% of the time it probably works. But there are a few cases in which it doesn't.
Right.
So,
So aluminum, that's going to be 3 plus,
uh-huh,
and nitrate is going to be 1 minus.
uh-huh. So when we break these compounds apart and put them back together, what's potassium going to go with?
That's going to go with nitrate.
Exactly.
So it's
Opposites
just,
attract, right?
right.
And so if it's not going to go with the negative phosphate, it's going to have to go with a different negative. Right. So in this case, because potassium is a positive one and nitrate's a negative one, you just need one of each. What about the other one? What's the other compound called?
Uh, yeah, it's the same situation. It's just aluminum phosphate.
Uh-huh.
Yes.
Yeah, because it's a positive 3 and a negative 3. It's just AlPO4, right?
Right.
Now, what's the charge of potassium? Or rather, what is the... Now, after you predict the products, you now have to identify what type of... whether or not it's soluble or not, basically. Because you start with 2 solutions, and that these are both aqueous. You have to figure out whether or not they're soluble or not. And for that, you may end up having to reference a solubility table or solubility chart. Okay?
Okay. I'll
Do
pull
you
one up.
happen to have a solubility chart?
Well, I have one on the internet.
I actually created a very nice solubility table. I hope I still have it. Here it is. Yep. I'm going to go ahead and post the link into the chat
Yes,
so you can
please.
pull it up and have it ready for you. Here's the solubility chart, solubility table.
So
So
it looks
is
like it's
K,
going to be aluminum phosphate.
yeah, so KNO3, is that soluble or insoluble?
That's going to anything with potassium is soluble.
Soluble. So this is going to be an aqueous. If it's soluble, that means it dissolves in water, which means it's going to be aqueous. What about aluminum phosphate? Soluble or insoluble?
Insoluble.
And since it's
Yes.
insoluble, that means it's going to be what phase of matter?
Solid.
It's going to be a solid. Or in the terms of solution stoichiometry, we would call this a precipitate. A
Precipitate.
precipitate. Yes, ma'am.
I'm just going to quickly add to Ethan that you're correct that potassium ion is in the first column. So whatever potassium occurs with is always going to be soluble. And additionally, nitrate also is a always soluble anionic compound. So whatever it occurs with also is going to be soluble. So it's the first species is double soluble is because of both the cation and the anion. So yeah,
Do you guys have
that's
that
all.
chart memorized?
Pretty much.
um, well, yeah, it's yeah, yeah, it's practice and also um, um, yeah, I would say it's not so complicated. If we do a few, you'll see that it kind of comes naturally. And let me ask you this: are you allowed to use this chart when you're doing the homework or when you're doing the test, or do they expect you to know it?
That's a good question. We are allowed a one-page formula sheet for the test, so I'm going to go ahead and take that as a yes, but I don't know for
Okay,
sure.
got it.
Yeah.
Yes, yes. So the answer is yes. Gotcha. Thanks.
So it can be tricky. But yeah, a lot of times professors will require you to memorize it. I know my professor did, but some professors won't. Sometimes will allow you to use it. So I mean, it's not really a big deal either way. But after working with
Is
it
there a
for
way
a
to
while,
predict? I'm sorry, my bad.
no, go ahead. Is there a way to
Is
predict
there a
what?
way to predict if something will be a gas after a reaction like this? Or does that ever happen?
Okay, so there are a few things that tend to form gas. Um, in a double replacement reaction like this, and these are actually things that you are going to actually need to know for your lab and for your lab midterm. Or maybe not your midterm, but definitely your final. Essentially, if you ever have H2CO3, which is carbonic acid, if you ever have this form as a product in a double replacement reaction, this aqueous acid is very unstable, and so it will oftentimes just break down into carbon dioxide, which is CO2 gas, and
Right.
water. And this is in fact what happens when you open a can of soda. The little bubbles that are coming up are carbon dioxide.
How cool.
And basically, and that's why soda burns when you drink it. Like if you drink a Coke, it
Uh-huh.
burns as you drink it. It's because it's an acid. You're drinking acid.
Is it carbonic acid?
Yeah, it's carbonic
Yes.
acid.
That is so cool. That's awesome. I love it.
Now, on the other hand, if you also there's a similar molecule that will also break down. This is sulfurous acid H2SO3. If this ever forms, actually I should put this actually as a single arrow. This is not a double arrow. This will also break down, and it'll break down in a similar way. It'll break down to water and sulfur dioxide gas. And then there's another thing that forms that will also be a gas. If you ever happen to form H2S,
Oh, the
H2S will
wonderful,
also be gas.
wonderful
Yeah,
smelling. Yes, the wonderful smelling, conspicuously smelling
yeah,
gas.
yeah. It smells like rotten eggs. Yeah.
Yes.
And then of course, yeah, Dr. Neely was saying that tongue in cheek about the wonderful smell of H2S. And then, uh, if for example, there's also a possibility, like for example, if you have an NH4 ion that gets neutralized in the presence of OH minus, you will find actually what happens here is that you end up with ammonia. If you get NH4OH, that'll break down into ammonia gas and water.
And you also in lab distinctively you will recognize it, and hopefully you're doing it under the hood because it's very corrosive and it really burns the eyes.
Yeah, very true. So yeah, so those are the common ones. Those are the things that can happen that'll form a gas. But generally speaking, you don't deal a whole lot with gas formation and double replacement reactions per se. That's usually something that more comes into place when you start getting some of the redox reactions and or certain other reactions as well. But uh, double replacement, usually it's just those types of the ones that I've shown above that will tend to actually decompose. Okay, cool. So now we need to balance our equation that we've just predicted the products for. So predicting the products is the first part. Now we need to balance it. So what do I do to balance it?
Uh, well, I think I'm going to start with potassium,
Good call.
Yes.
and so I'm just going to put a 3 for the coefficient of potassium nitrate.
Mm-hmm. Yeah, good.
Um,
And it turns out that's all you need. Yep.
oh, yeah. Cool.
So that will balance it. So
Good
now
job.
here's the tricky part. We got to break each of these substances up into their component ions. So what will K3PO4 break apart into?
K3 positive and PO4 3 minus.
Not exactly. when you see K3, that actually means that there's 3 potassium ions. So the 3 goes in front, not as a subscript. That's
Okay.
3K
I didn't
plus.
know that.
Mhm.
So, okay.
Now, that's one mistake that students often will make, is that they'll put the subscript down there. They'll think that 3Ks stay together. Once they realize that that's not the case, then they tend to make a different mistake. What do you put for the, what happens to the PO4? What does that become?
I'm just going to say PO4 3 minus.
And that is correct.
Yes.
Okay.
A lot of students will sometimes try to separate the oxygen from the phosphorus, and you can't
So
do
why
that.
doesn't it?
The reason is because phosphate is actually a um, okay. So phosphate is actually a covalent compound that has a charge. So phosphate actually looks kind of like this. Okay, it has shared pairs. You're actually going to understand more about this when you actually do Lewis structures later on. But this is the Lewis structure for phosphate, and effectively, these are bonds. These are chemical covalent bonds, and covalent bonds actually actually tend to be stronger than ionic bonds. They bind the atoms together more tightly. Okay, because ionic bonds are just a force of attraction between positive and negative charges, but covalent bonds are formed by the sharing of electrons between 2 atoms, and that sharing really requires kind of a closer connection between the atoms. So in this case, the negative 3 charge is actually split between these 3 oxygens here, but the overall molecule has a negative 3 charge. So this whole thing, which is chemically bonded, is not really separatable, at least not easily. There are certain chemical reactions that can break it apart, but generally speaking, this has to be treated as a whole. It doesn't actually separate very easily. It's one covalent molecule. Yes?
Yeah, that's cool.
Uh,
Sounds good.
yeah, yeah. Actually, a tiny correction here. The ionic bonds are stronger than covalent bonds because of the difference, the huge difference in the electronegativity, and that's why we deal with lattice energies that are so huge. So as far as strength goes, the ionic bonds beat the covalent bonds.
Huh. I had been told differently just because with like if you look at network covalent structures, like for example diamond and things like that, those crystal structures that are composed of covalent bonds require temperatures in the thousands of degrees Celsius in order to melt. Where, because to melt it, you really have to break those covalent bonds. Whereas if you have an ionic substance, that its melting point, the crystal structure breaks down more easily because the melting point is much lower. Usually I mean, it can depend upon the substance, but a lot of times it's in the hundreds or below 1,000 degrees Celsius, sometimes a little bit above. So I had been told that the reason that that is the case is because covalent bonds are actually stronger. But yeah,
Well,
I mean, it is one of those tricky things. So, I mean, maybe I was informed incorrectly.
yeah, I mean that no, that's okay. I guess I can look at some examples and then just find a trend, and then if we remember and we're interested, we can tackle it next time because it's fun.
Yeah, no, absolutely. That's definitely a good thing to look into. Um, it's one of those really interesting facets of chemistry, like when we talk about relative strengths of bonds. So yeah, let's definitely revisit that. So
Oh,
PO4 3 minus. So this is an aqueous. So anything that comes from aqueous is aqueous. So that's an important thing to note. That like when you're translating a molecular equation, which is what the first one was. That's what's considered the molecular equation. When you're translating a molecular equation into an a complete ionic equation, anything that came from an aqueous compound is still aqueous when you break it up into ions. Okay, so what's next?
Aluminum 3 plus aqueous.
Got it. Got aluminum 3 plus.
And then 3 nitrate minus, which would also be
Exactly.
aqueous.
Yeah, even though the NO3 doesn't break apart itself, there are 3 NO3s. Yeah,
Yes.
very good. And then we go ahead and we draw the arrow to the product side. And what happens to the product side?
Oh boy. I think 3K or 3 potassium plus.
Yep.
Yes.
And then
So the coefficient will multiply everything in front of it. So absolutely. 3K plus aqueous. And what else?
3 phosphate 3 minus aqueous as well.
3 phosphate.
I'm sorry, nitrate. I wrote it down.
I thought you meant nitrate. Aqueous. Okay. And then what else do we put?
Aluminum phosphate salt.
Ah, yeah, we don't break that apart because
Good
solids
job.
Yay.
do not. Yeah, it's a precipitate. So basically, the ionic bonds are so strong in aluminum phosphate. The attractions are so strong between the ions that the water is just not really capable of pulling them apart effectively. Now, you'll find out later that it turns out that there's no such thing as a completely insoluble ionic solid. There always will be a little bit that breaks apart, but it's going to be a pretty small amount. It's going to be a small amount, very small amount. All right, now for Net-Ionic equation. Now all you have to do for the Net-Ionic equation, so this is the easy part, is identify anything that's present on both sides of the complete ionic equation and cancel it out. So what cancels out here in the complete ionic equation?
Well, how about both 3 potassium plus on both the left and the right?
There you go. And what
Both
else?
nitrates, so 3 nitrate minus and
Absolutely. And so we're left with the net ionic equation, which is basically just Al3 plus aqueous plus PO4 3 minus aqueous, and that gives us AlPO4 solid. So now for part B.
Yeah, okay. Yeah, I was just going to say, yeah, looks good. Thank you.
All right, cool. So what would be the first thing you'd have to do with something like this? What do you think, Ethan? Or we actually have a new guest. Hello. So either one of you can definitely take a stab at this. Just let us know, and feel free to turn on your microphone if you would like. That would be totally welcome. So what
Thank
type
you.
of
I'm totally taking this all in. I'm just like writing as many notes as I can.
Oh, no problem, no problem. So thank you for joining us. So what type of reaction would this be? Because this is the first thing you should really look at when you're trying to predict the products of any equation, much less doing with the Net-Ionic equation. What type of reaction would this be, and how do you know? And it's okay to say if you don't know. That's okay too.
I'm totally looking at the solubility chart too. I'm at it.
That's a good that's a good idea. What do you think, Ethan? Do you have an idea of what type of reaction this might be?
I'm inclined to believe it's single replacement.
Very good. Yeah, this is definitely a single replacement reaction. So in this case, since it's a single replacement reaction, the first thing we probably want to do is identify what types of species we have, and if it's an ionic compound, identify the ions. So what would the charge of the chromium be in this compound? The chromium nitrate.
It would. I mean, it would be forced to be. Uh, well, this chromium is minus. Or no, wait. I'm sorry. This chromium is just positive. But
It's
there's.
positive.
Yeah, let
But
me show you a trick. Let me show you a trick because chromium is one of these metals that we don't obviously know the charge of it. So the
yeah,
easier way is to figure it out, and you use the charge on the polyatomic ion to figure it out. So how about we start with determining the charge on nitrate.
1 minus. So it's chromium 3 nitrate.
very
Yes.
good. Yeah, there's 3 nitrates. That's a total of -3. So to balance that, chromium has to be the opposite, a +3. Very good.
Gosh, I don't know why we do that in chemistry. That's so weird.
Thank you, Dr. Neely. Yeah, good call. Look at the ion it's bonded to figure out what a transition metal is, because you can't just tell with the periodic table. All right. Now, I don't have to worry about a charge with barium, because barium is a solid right now. But if barium did have a charge, if it was part of an ionic compound, what charge would it have?
It would be 2 plus.
So I'm going to actually put this in parentheses because it doesn't actually have the charge now, but as part of an ionic compound, barium would have a 2 plus charge. So if this is a single replacement reaction, what switches places with what?
The metals will switch places.
Metals will switch places, which means that barium is going to go with what?
Nitrate.
Nitrate. Metal switch places. So chromium gets kicked off on its own. Chromium gets the boot. And barium goes in its place. So, that being the case, we're going to have,
Barium nitrate.
and what's the formula going to be?
Oh shoot! Dang it! It's gonna be barium nitrate with a 2 on the outside of it.
Exactly. When you put it back together, you have to put it back together according to the charges. Barium's a 2 plus, nitrate's a 1 minus, so I'm going to need 2 nitrates for every 1 barium. Now, is that soluble or insoluble?
It's nitrate, so it's soluble.
Mm-hmm. Now, as far as the chromium's going to get kicked out on its own. Well, if it gets kicked out on its own as a metal, that means it's going to be what phase of matter?
I guess depending on temperature, but I'm gonna say solid.
Yeah, in all likelihood, it's be a solid. There's only one metal that I know of that is actually at room temperature a liquid, and that's mercury.
Yes.
Mercury. Okay.
There's another metal that gets room temperature very close. I mean, that's a liquid at very close to room temperature. That would be gallium, I think. I think gallium will actually
it's gallium. It'll melt in your hand, right?
Yeah, it'll melt in your hand. It's
I've
kind of
seen
fun,
that.
actually. If it wasn't so darn expensive, it'd be kind of cool to bring into the classroom and just be like, yeah, it's not really, it's not like super toxic or anything, so you can actually just kind of play with it.
Only a little bit of a carcinogen.
Yeah.
Those metals, yes. And gallium is heavily used in the semiconductor industry, in the chip industry. Its use became very prevalent when the microchip industry started to skyrocket.
Oh, that's interesting. I didn't actually know that. Yeah, good information. I feel like I should have known that, but I didn't. That's cool. All right, complete ionic equation. Let's break this down. So, what gets broken down on the reactant side?
Chromium. Well, okay. Well, I guess it's chromium 3 positive,
Uh-huh.
nitrate 1 minus, or 3 nitrate 1 minus, or just minus.
But before we do that, what do we need to do to this equation?
Oh, balance it.
Yeah, we need to balance it first.
So I think it should be 1, 3, 3, 1. Oh, no, that's wrong. No, don't listen to me. Maybe 2, 3, 3, 1. No. 2, 3, 3, 2.
Yeah, it is 2332. Effectively, what it comes down to, though, is if you're listing these out to try to balance them, you have a CR, N, O, and a BA. And this is for the benefit of our other guests. Uh, do you want to take the time to look at how to balance this, or do you feel like this is you already know how to do this? What do you think, Daenerys?
So yeah, so we take each of them apart, and then I was looking. I thought it was, what is that? 2, because the NO3 is 2 on the other side as well. I mean the N and the O. So I'm breaking them down with you.
Yeah,
Now it's fine to break it down, but I would not have broken it down. I would have said nitrate, we have nitrate both on the left-hand side and the right-hand side, and there's no separation of the atoms of nitrogen and oxygen anywhere else. So I would have kept it as one unit, but this works as well.
yeah. I, and I used to. I have to confess. I used to do that too. But what I started noticing, especially like if you're looking at redox equations and things like that
Uh-huh.
sometimes the nitrate just starts to break down, and sometimes it does, sometimes it doesn't, sometimes it's obvious. And I just
Uh-huh.
realized, if you it actually doesn't require any additional work to do it element by element. So I just started to do it that way.
Got
I
it.
just felt like it felt like it's easier. But I do, I mean, definitely respect that point. You could definitely keep them together. That is absolutely true. Now,
Uh-huh.
chromium and barium are already balanced here, but I think the key thing is to recognize when you have an odd number that you're trying to balance with an even number, like the 3 with nitrogen and the 2 on the nitrogens on the other side. When the odd number balancing with an even number, you double the odd to make it even. How do I double the number of nitrogen atoms on the reactant side?
Asking me?
Yeah,
Sorry.
well, I'm asking
It's times
anyone.
2.
Yeah, you just put it to a coefficient. So if you do that, you get 2 chromiums, and then, of course, your nitrogen becomes 6, and your oxygen becomes 18. From there, I can now balance everything else on the other side. So I want a 2 chromiums on the other side, so bam, there's 2 chromiums. I want to balance the nitrogen, so I have 2 and 6. So what would I put in front of the barium nitrate?
3.
3. Very good, Daniel. Awesome. You got a 6
Yes.
there. And then, of course, 3 times 6 is 18. 18 oxygen. And then I have 3 bariums. And then all I have to do is balance the barium, and I'll put a 3 here. So maybe that was unnecessary to go through that, but I just thought it might be helpful.
Yes. Thank you.
No problem. All right. So now let's break down the complete ionic equation. All right. And we had already started. So how many? So what does this break apart into then?
2 chromium 3 plus.
Uh-huh.
3 nitrate. Oh wait, no, 6.
Yeah, 6 nitrates. Very good.
6 nitrate minus. Oh, both of those are aqueous. Yeah, I forgot to say that.
It came from aqueous, so it's aqueous. Yep.
I have never done a complete ionic equation with single replacement. I have no idea what to do with barium.
Well, barium's a solid, right? So it's not an ion. So I just leave it
Yeah,
as
but
it is.
it's so weird to me. I don't know why.
The only so the key thing is when you're converting a regular molecular equation into an ionic equation, you have to break up every soluble ionic compound and every strong acid. In other words, you break up any strong electrolyte. You only break up strong electrolytes, and strong electrolytes are two categories. There's only two categories of strong electrolytes. There's soluble ionic compounds, and there's strong acids. Only those two. So if it's not a strong acid or a soluble ionic compound, then you don't break it apart. So a gas, leave it alone. Solid, leave it alone.
So if on the left we have an ion that is 3 barium solid, but on the right we had 3 barium plus that was aqueous, do those two mark each other out?
No, they don't. Because on the right hand side, the product side, the barium is actually an ion. And because it's part of an aqueous compound, it is aqueous. So neutral barium solid metal is not the same as barium ion. Those are two
Right.
chemically distinct species. So what else would be there besides the barium on the product side?
How about 6 nitrate minus
Yep, 6 NO3 minuses. And
and
what else?
2 chromium solid?
There you go.
And maybe just a little bit more elaboration on the solid phase of barium versus the aqueous phase. I don't know if barium is one of the trace elements that we need. We don't take supplements obviously with barium, I don't think. But for example, if we take another metal like magnesium, it's common for people that don't eat properly to take magnesium supplements. Those
Mhm.
magnesium supplements, they're when you dissolve it in water, you end up with magnesium ion, which is drinkable. You can drink it. We are not eating solid magnesium, so it kind of shows that the phases are critical and they are distinct.
Hmm.
Yes,
And technically, yeah, go ahead, sorry.
oh, sorry. I just had a question. If you had like an idea of what like a barium swallow, because I know they do that a lot with like swallowing disorders. Like how,
Oh
Yeah,
yes,
that's basically the barium shake, basically. Um,
yes,
what they use that for primarily is to do an imaging of your digestive tract. So they'll
yes,
give you
very
like a barium shake, and
yes,
because barium does actually absorb X-rays and other types of radiation, whereas in your normal body tissues it'll just pass through. It'll actually be able to give you like an image, or it'll be able to track. Um, it'll be able to give you a movie of showing what's happening in your digestive tract as the barium is going down, is going through you, and can help to diagnose different problems you might be having.
very good point. Thanks for the clarification, Danira.
thank you. I was just asking because I know like dysphagia, they use that with that. And so we were talking about it being a solid. So I was trying to get a picture. Thank you.
Yeah, no problem. Yeah, and that the barium shake is actually, I think, barium sulfate, if I
Yes, it
recall.
is sulfate,
Yeah,
correct.
and that's a precipitate. That's a solid. But it's an ionic solid. It's an insoluble solid. You look at sulfate on your solubility chart. you'll notice that it's normally soluble except with barium.
Got it.
Yes.
Thank you.
Yeah, so what cancels out here?
It looks like it's just going to be 6 nitrate and yeah, 6 nitrate.
Mm-hmm.
That's really lame. I wish it looked a lot cleaner than that. I've never seen aqueous ions on the right side before. That really throws me off.
Really?
Yeah. I don't know what kind of problems she's been having us do, but I've never seen it.
The truth is, this is actually a very common type of reaction equation that's shown. This is a very common type of reaction equation that's shown in electrochemistry. Electrochemistry, a lot of times, a lot of these half cell reactions, or a lot of these wet cell reactions will involve the transfer of electrons from one metal to another across a wire. And that causes the generation of electricity in batteries. So,
Yes.
um, so this is actually, yeah, these type of reactions are actually quite common.
You're all set when you take general chemistry too, because you'll see that a lot.
Yep, very true. You may even see it to a certain extent in the lab, because I think, I mean, in lab this semester, because I think there is a lab that deals with some of these single replacement reactions, if I recall correctly. These are the simplest type of oxidation reduction reactions, and sometimes they introduce this early on.
Cool. Sounds good.
Cool. You want to take a stab at the next one?
Oh, okay.
I'll go. We'll go ahead and give it to you, engineer, to work out. Go ahead. We'll give you a few minutes to come up with an equation, just the normal equation, not the complete ionic yet. Just we'll start out with just predict the products, write a balanced equation, and identify the phases, and then we'll check it together in just a minute or two. Okay?
Cool.
You can go ahead and raise your hand when you think you have an answer, like this. All right, good job. Ethan's got it down. Now we just need. How about you, Janelle? Do you need any more time, or would you like to just kind of go through it?
We can go through it. I've written a lot down. I just want to go through it.
Sure, no problem. All right, so let's go ahead and take a look. All right, Ethan, tell me what you got. I'll be your transcriber,
Okay.
stenographer.
About MgS, because obviously
Yep.
that's magnesium sulfide, but that doesn't get us anywhere. Me just saying that.
What about the What about the phase?
I believe it to be aqueous.
Oh, no, it's not.
What? On your table it says
Sulfide?
sulfur.
S2 minus? Sulfide?
Yeah, because it's except group 1A and group 2A. Group 2A, isn't that your alkaline earth metals?
Which
Is
is
that what it says? I thought magnesium sulfide was a solid, but if that's what it says, maybe it is aqueous.
I mean, I have not been doing chemistry long enough to know.
now. Let's see. The magnesium occurs. It's an alkali metal. Let's think about it. Alkali metal, and it's occurring with a sulfide. No, I believe that's a solid. Let me check.
So I wonder what that 2A means.
I said it's a white crystalline material, but it often is encountered in pure form, generally produced by production of metallic iron.
Oh, you know what? It's one of those dumb ones that's like slightly soluble, isn't it?
Oh, oh,
Let's see here.
No. So, okay. So
Sulfides are
it
generally
apparently. So this is weird. So this is kind of a loaded question. We're gonna go ahead and follow the rule, the chart, and say that it's aqueous. But the truth is that magnesium sulfide is actually something that when it reacts with, or when it hits water, it automatically reacts with water. Okay, forms H2S. But we're gonna say it's aqueous. Okay, we're gonna pretend just because that's what the chart said. And we're gonna chalk this up to my lack of knowledge, not preparing properly. All right. All right. So So what is nitric acid then?
That's just going to be HNO3.
Okay, good.
I can tell that if we treat this magnesium sulfide as aqueous, it's just not going to work out. I think it's better to treat it as solid because
Oh no, it'll still work out. It'll still work
uh,
out. So HNO3, is that aqueous or not?
It's an acid, so I'm going to assume it's aqueous.
Yeah, acids are always aqueous. It's a strong
Yeah,
acid too.
so according to Flynn, magnesium sulfide, there's not enough data to be able to say it's soluble or insoluble.
Yeah, that's because it reacts. It reacts instantly whenever it touches moisture. So,
good
Cool.
job.
what charge is magnesium?
It's 2 plus,
hmm What charge is sulfide?
2 minus,
And what charge is hydrogen?
1 plus,
hmm
or
And what
plus,
charge is nitrate?
minus.
Yeah, 1 minus. So, if I do this is what type of reaction then?
Double replacement.
Double replacement.
Yes.
And therefore, what will the products be?
Magnesium nitrate and what is that? Is that dihydrogen sulfide?
Dihydrogen sulfide. And actually, truthfully, even though technically speaking it is a covalent compound, and even though technically speaking, I mean, you would think that it would be dihydrogen sulfide, it's typically just referred to as hydrogen sulfide. And what
Is
is the phase of matter of hydrogen sulfide? Remember, we kind of indicated this above.
it
When you see H2S formed, that means H2S is going to be a
gas?
yeah. There you go. It's going to be a gas. So we're going to put a little gas here. And what else is going to form? You said magnesium nitrate. What's the formula for that?
MgNO3 too.
Yeah.
Okay, well
There we
it's
go.
not. If it's balanced and stuff.
So is it balanced?
Well, not yet.
Okay. And is what phase of matter is magnesium nitrate? Is that soluble or
Uh,
insoluble? What are you looking at?
Soluble.
Okay. And now we balance it. So what needs to happen to make it balance?
I think it just needs a 2 in front of nitric acid.
Very good.
Yes.
So now let's draw. Now that we have that, is that what you got, Janier?
Yes, I can see why.
Awesome. Good job. So now we just need to break it apart, whatever is appropriate to break apart. And so what would this give us?
Mg 2 plus aqueous.
Uh-huh.
Sulfur 2 minus aqueous. 2 H plus aqueous. 2 nitrate minus. And then the reactants would be 2 magnesium 2 plus Yeah, right. And then plus nitrate minus, and then plus uh, hydrogen sulfide. Since it's a gas, I assume it can't be split into ions into water.
Exactly. Well, I mean, technically speaking, it can be split into ions, but I mean, well, gaseous, it is possible to split things into gaseous ions, but that usually requires quite a bit of energy, and it usually doesn't happen with something like hydrogen sulfide. So, because that's a covalent compound. All right, so yes, you arrow to the products, and you have hydrogen sulfide gas that stays together, and then what else do we form?
It's going to be 2 magnesium, 2 plus, and
Two magnesium, two pluses?
no, no, it's going to be 2 nitrate, 1
No.
minus.
So one magnesium, two plus,
Right.
and two nitrates. Very good. All right, cool. And what cancels out, if anything?
It looks like magnesium and nitrate.
Okay. And you're right. Magnesium and nitrate do cancel out. And we're left with a net ionic equation of S2 minus aqueous plus QH plus aqueous goes to form H2S gas. Now, coincidentally, I want to say that Dr. Neely is right that the in actuality, the only way that this reaction would happen, or not H2O, the only way this reaction would actually happen in real life, or the only way it could happen, is if you had solid magnesium sulfide reacting with nitric acid.
Right.
Because if you you wouldn't ever get aqueous magnesium sulfide because magnesium sulfide reacts with water automatically to produce hydrogen sulfide gas and magnesium hydroxide.
Thank you for the clarification, Professor.
Yeah, no problem. I got to give credit where credit is due. There we go. Yeah, that's good. So this is how you would break down these net ionic equations. First, write and balance the molecular equation. Second, write out the complete ionic equation. And third, cancel out the common ions in order to figure out the net ionic equations. Now, these ions that cancel out in each one of these complete ionic equations, what are they? They have a special name. What are they called?
How about electrolytes?
Well, actually, and that's not entirely true. They are electrolytes.
Right.
But what are they called in the context of the reaction? What do we call people who watch sports?
Spectator ions.
Yeah, there you go. What do you call people who watch sports but don't actually play them? Spectators, right? So these are spectator ions. Spectator ions. They just kind of sit back and watch the reaction happen, but nothing really happens to them. All right, cool. So that brings us to molarity. Now, molarity is the most common type of concentration that we deal with in chemistry, and it is also one of the most useful by far. Molarity is the number of moles of solute or moles of dissolved substance divided by the liters of solution. So um, this definition is also an equation that can be used, but there's also a principle here that if you like, for example, if you rewrite this equation, you can say that the molarity times the volume, or times the liters, basically. Molarity times the volume in liters is going to give you the moles. There is a case in which, and that happens a lot in chemistry, where we dilute solutions. And we're basically, all we do to a solution is add water. If we add water to a solution, do we change the number of moles of solute present?
No.
Exactly. You don't change the number of moles. So that gives us, that recognition gives us this dilution equation. And the dilution equation has some related equations that actually are useful as well. And that dilution equation is this. M1 V1 is equal to M2 V2. Does that make sense?
I didn't know that's where that came from. That's amazing.
Mm-hmm. Yeah, so and M1 V1, technically speaking, M1 and V1 can either be the initial undiluted concentrated solution, and M2 V2 can be the diluted solution, or you can do it vice versa. But the important factor is that M1 and V1 have to correspond to the same solution. So either M1 and V1 have to both be the diluted solution, or M1 and V1 have to both be the concentrated solution. But yes, so M1 V1 is equal to M2 V2. One side's the diluted solution, one side's the concentrated solution. Now in this particular example here, so the person suffering from hyponatremia has a sodium ion concentration in the blood of 0.118 molar and a total blood volume of 4.6 liters. What mass of sodium chloride would need to be added to the blood to bring the sodium ion concentration up to 0.138, assuming no change in blood volume?
This is a fun problem.
Mm-hmm. So the interesting thing is here, even though I went ahead and showed the dilution equation and I also showed the molarity equation, which equation would be more appropriate to solve this particular problem?
I feel like it's going to be M1 V1 equals M2 V2.
Is the blood being diluted?
Yeah, and just the trick here is that it says assume no change in blood volume.
Mm-hmm.
Well, I guess my thought there was, since M2 times V2, that's going to equal that whatever number I got right, I can just multiply by the molar mass of sodium chloride. But I guess
The key word here is dilution. The only way a dilution equation can be used is if the only thing being added is water. Is water being added to the blood? Yeah, it's the sodium chloride that's being added to the blood, right? And sodium chloride is a solute. And since sodium chloride is a solute, I can't use the dilution equation because the number of moles is changing. The final number of moles is not going to be the same as the initial number of moles. Does that make sense?
it does, but now I'm lost as to what to do next.
Okay, well the key thing is what you need to do is you need to find the amount that's present initially and the amount that needs to be present at the end, and then figure out what the difference is. And so for this is you can use molarity as a conversion factor. So to do that, you can take like I know I have 4.6 liters of blood, right? Well, I can
Yes.
convert liters to moles using the molarity. So let's start with the
Right.
initial. So let's start with the initial. And I'll use I'll use a squiggly line here, and then I'm gonna use a different color to outline. This is initial. Oh, I thought I had a different color. So this is the initial. So the initial blood concentration of sodium ion was what?
0.118 molar.
Yeah. So I could, since it's 0.118 means it's 0.118 moles per 1 liter. Molarity means moles per liter. In fact, the use of a capital M for molarity is, at least as far as I think, I mean, correct me if I'm wrong, Dr. Nia, because you might know better than I do, but I was under the impression that the use of capital M for molarity was a relatively recent, within the last 30 years or so, convention. That prior to that, it was generally molarity was generally written as moles per liter, like that.
Well, I have to say your history knowledge here beats mine. Yeah, I mean, I guess I've been so used to using them interchangeably, but interesting history. So it's about 3 decades that the capital M has come about. Interesting.
Yeah, and I think I mean, at least I think that that's correct. Like I think I recall that, but sometimes my memory is a little bit shaky. But the idea is, chemists are sometimes lazy, and so sometimes we'll take two units and just combine them into one unit just to make it easier on ourselves. And so the moles per liter became capital M. But we can use it as a conversion factor. 0.18 molar is 0.118 moles per liter. And then that means that the liters is going to cancel out, and I can calculate the moles. And how many moles of salt does how many moles of sodium ion does the person have in their blood to start with?
0.54.
Yeah, so I know, yeah, 0.54 moles to start with, and that's moles of Na plus. Now, we also have to figure out what would the final amount be. So what would the final amount be? Let's do a different color. Let's do this one. Final. I'll go back to my red. Okay,
I think it's going to be 0.63 moles.
that sounds about right. 0.13, and you use 0.138 moles per liter, right?
Yes.
And so this is you said 0.63?
Yeah, if you're including significant figures.
Mm-hmm. So this is what you start with, and this is how much you need to get to. So what you can do is how much do you need to add then?
About 0.0920 moles.
Yeah. So we tend to round at the very end. I know we only have one significant figure here, but yeah, 0.920 moles or something. This is moles of sodium ion. But of course you get moles of sodium ion Na plus. So from that I can go ahead and convert. I know that for every 1 mole of sodium ion, I'm going to need 1 mole of sodium chloride, right?
Right.
And then from there, I can convert moles of sodium chloride to grams using the molar mass. So 1 mole of NaCl is equal to the molar mass, which is 58.44 grams of NaCl.
Dang, I did it wrong.
How so?
I just used sodium for some reason.
Oh, because it asks how many grams of sodium chloride would have to be added.
Right, I think
Because
I
sodium
just
ion doesn't
salt.
exist in isolation, right? You can't just get sodium ion by itself. You have to have it bound to something or connected to something. Un, um, Positive charges and negative charges in large quantities are actually very unstable and even explosive. And in fact, um, new research on the reaction involving sodium with water has revealed the fact that what causes the explosion when sodium metal is put into water is actually not the ignition of hydrogen gas that's formed, but rather the explosion is caused by the a dis an power a really really strong and potent imbalance in charge resulting from the rapid transfer of electrons from the sodium to the effectively to the hydrogen and forming the hydrogen gas. And so that massive transfer of electrons leaves you with a large number of positive charges all in one place, and that causes the explosion. And those explosions can be very significant. So, um, unbalanced charge is very dangerous, and that will cause explosions. So it's like you can't just like shoot somebody up with like sodium ion by itself. One, the sodium ion itself would probably explode if it was like all concentrated without any negative ion to stabilize it. But two, I mean, if you just don't find that in nature to begin with, so you'd have to use
That's it.
some sort of benign compound. Oh, sorry. Go ahead, Dr. Neely. My apologies.
Oh, yeah. And like you said, Professor Deba, you do not find that in nature because for every anion, the counter ion, which is a cation or vice versa, has to be present in nature because nature is molecularly neutral.
Yeah, and and, and I'm not entirely sure, but I'm pretty sure I'm right about this, and you can correct me if I'm wrong, Dr. Neely. But one of the issues where you have batteries exploding and things like that happening, a lot of time that's due to charge imbalance because if these electrochemical cells get off kilter and electrons are being transferred, um, but there's not appropriate like salt bridge or the effective equivalent of that to neutralize whatever charge is being passed over, you can get an imbalance which ends up causing explosions.
Okay, so I don't know that. I'm going to look into it. I'm going to take your word for it now. But the explosions that we hear up for in the laptops or these are lithium-ion batteries,
Hmm.
and yes, okay, interesting.
So, all right. So then, what do we get for our grams of sodium chloride that we have to add?
It's going to be 5.376 grams of sodium chloride.
Mhm. And with one significant figure like we have here, there end up being 5 grams. And there we go. Cool.
Very
Now,
interesting problem.
oh yeah, very much so. Now, as far as the concentration in each of these ions present in the solution formed by mixing, this is a little bit of a tricky problem, but it's not necessarily one that is common that I've seen professors go over very much in classes like yours. So I'm just going to go ahead and skip it. And the reason I'm going to skip it is because um, I want to get to some things that I think would be a little bit more effective for your purposes. Um, I'll skip C as well. Yeah, skip 3, A, B, and C, and we'll go to number 4. How many milliliters of 0.12 molar HCl is needed to completely neutralize 50 milliliters of 1 molar hydroxide solution? So here's where you actually have to write a balanced equation. HCl is going to react with the barium hydroxide.
So I don't know about everybody else, but I lost the screen.
Me too.
Oh, uh,
Can everybody else see this, Danira?
No,
I got.
ma'am.
It says it says I got disconnected for a second. I don't know why. Here we go. How's that?
Yes, thank you.
Perfect.
All right. So the barium hydroxide and HCl react, and what? And this is once again, this is what type of reaction?
Double replacement.
Yeah, it's double replacement. There's also a special name for this particular type of double replacement reaction. When you have a acid reacting with a base, it's called neutralization. So what would the products be in this case?
Be oh wait, I guess just water and barium chloride.
Uh-huh. Yeah, a neutralization reaction typically has water as one product, and the other product is a salt. And the salt is going to be, in this case, barium chloride, BaCl2. Very good. And now we just have to balance the equation. So, how do we do that?
Uh, it we need a coefficient of 2 on the first reactant.
Mm-hmm. Very good. Identifying chlorine
And
present in both.
good, maybe? No, we need a 2 in front of the water,
Mm-hmm. Yeah, and
which
this is
means we
an
need a
interesting
4.
one. I'm sorry.
I was going to say that means we also need a 4 in front of the hydrochloric acid now.
Nope.
What? Oh, because of. Never mind. Sorry.
Yeah. So this is this this is a perfect example of why you want to identify the element you want to balance first before you start balancing. And the one elements you want to balance first are those that appear in the fewest compounds. Hydrogen note appears in 3 different compounds here. It is the last thing that you want to balance. So that was smart that you went to chlorine first, because chlorine only appears in 2 compounds, and therefore you want to balance that first. Now barium also appears in 2 compounds, so to balance that, but that already is balanced, there's 1 and 1. And oxygen also only appears in 2 compounds, so oxygen, normally you wait to blast to balance oxygen, but it turns out in this case, you'd actually balance oxygen before you would balance hydrogen. So chlorine comes first, you balanced it with the HCl, and then oxygen would be the one you would balance next, if you're careful. Because in this case, now I have 2 oxygens on the left side, and so I would need a 2 in front of H2O. And then from there, you'd see that the hydrogen was already balanced. That would be the easiest way to look at this.
Yes.
Cool? All right, let's rock at this, okay? We have 50 milliliters, so 50 milliliters. And milliliters gets converted to, what am I going to have to convert milliliters to?
Liters.
Liters. Yeah, because remember, molarity is moles per liter, right? So I can use molarity as a conversion factor to convert between moles and liters, but if I don't have a liters, can't do anything. So I convert the milliliters to liters. I can do 1,000 milliliters equals 1 liter. Alternatively, I could write 1 milliliter is equal to 10 to the negative third liters. Either one of those is valid. What unit comes on the bottom of my next conversion factor? What needs to cancel? What comes here?
Liters.
Liters.
Yes.
So it's
And
going
then
to be
what can I
moles on the
convert
top.
liters into?
Moles.
Moles of what?
Oh, I guess this is going to be barium hydroxide.
Now, how do
Yes.
you know it was barium hydroxide and not HCl?
By reading the problem.
By reading the problem. Good. Yeah,
Yes.
because it says I can't start with the molarity because molarity is a conversion factor. I'm not going to start with conversion factor. So I ended up starting with the 50 milliliters, but the 50 milliliters is of the 0.101 barium hydroxide solution. The 50 milliliters is not of HCl. So this I can't write HCl here. I have to write barium hydroxide. I think it's funny how you said it by reading the problem. But you know, some people read the problem and they just don't see that. That's not totally obvious to them. And
Right.
that's really good that
Yeah, how
you're
about
able to pick that out. What'd you say?
I'm the person that doesn't typically read the problem.
Yeah. It's ironic that you found it. No, I was kidding. All right, so what comes on the bottom of the next conversion factor?
How about moles of barium hydroxide?
Very good. No, it's pretty much assumed that whatever was previously on top is what then. Now, it's important to always keep in mind and keep looking back at what we are actually trying to calculate. What are we trying to calculate here? What are we trying to find?
We need milliliters of hydrochloric acid.
Yeah, so I need milliliters of HCl. So before I can figure out milliliters of HCl, I probably have to convert to what?
How about moles of HCl?
Moles of HCl. And this is where the stoichiometry part comes into it. This is solution stoichiometry because we use the balanced equation to convert from one solution to a different solution. We're using solutions, so we're using volumes and concentrations, but we're also using stoichiometry because we need to use a mole-to-mole ratio. And this mole-to-mole ratio is 2 to 1, 2 moles of HCl to 1 mole of barium hydroxide. So now that I have moles of HCl, what do I do?
What goes on the bottom?
Well, moles of HCl.
Yeah,
Yes.
moles of HCl is going to go on the bottom. And what goes on top?
I guess just liters of HCl.
Yes.
Yeah, liters of HCl. Exactly. I I don't want to go back to any other substance. I need to get to the volume. And can I convert from moles to liters? Yes, because I have the concentration to do so. So what number goes in front of moles and what number goes in front of liters?
0.120 in front of moles and 1 in front of liters.
Yes.
Exactly. Moles per liter is always per 1 liter. Very good. And then from there, do I need to do anything or can I just calculate it?
Well, I mean, technically you need one more conversion factor, but
Yeah, that's right. I need to convert liters to milliliters, right?
Yes.
yes.
And so 1,000 milliliters is equal to 1 liter. Now you'll notice kind of interestingly enough that since you're going from milliliters to milliliters, these two, the front conversion factor here and the back conversion factor here are actually opposites and they actually cancel each other out. But that's neither here nor there. You could keep them in or you can take them out. It doesn't matter. But
So you,
multiply everything on top and divide by everything on bottom, and what do we get?
Uh,
Let me
point.
take you a second.
I think it's going to be. I messed up. Give me just 1 second.
No second. You tell me now.
Hitting the wrong button. Uh, 841 milliliters.
Nope, that is not right. 841 is way too much.
Is it 84?
84.1.
84.1, very good. Yeah,
Dang it.
84.1 milliliters.
And the reason Professor DePaul immediately was able to figure out that it's an order of magnitude off, and you can easily check yourself, is here you're working with 50 milliliter increments. So, you're going to have the same order of magnitude increments.
Likely. It's a combination of the fact that it's 50 milliliters to start, and if you look at the concentrations here, they're not actually that different. 0.120, 0.101 are pretty similar. So if it's 50 milliliters of the one, chances are you're going to need something not too off from the 50 for the other. There's a 2-to-1 ratio, so that definitely increases the amount. So it would make it closer to 100, but maybe not quite, and that's why you get the 84.1.
Right.
So I've found a pretty weird way to solve these problems, and I'm not sure
Oh,
if it's right or not.
we'd like to hear that. The weird
You
way.
explain your weirdness.
So, if I was asked to calculate the concentration of hydroxide in 0.101 molar of barium hydroxide, the concentration would be 0.202 molar, correct?
Yep.
So if I was asked to find the concentration of hydrogen ions in 0.120 molar of hydrochloric acid, it's going to be 0.120 molar. So this isn't quite right, I don't think, but you can actually use M1 V1, M2 V2
Yep.
and get
Yeah,
the answer by using those numbers.
yeah. No, that's correct. That's the acid-base titration equation. It's the
Oh, is it?
you see this sometimes. You have an acid-base titration. It's the molarity of. You actually can use this, and you don't even have to write the balanced equation for it if you do. The molarity of the acid times the volume of the acid times the number of H plus ions in the acid. I'll just put NH plus. So in this case, there's only one acidic hydrogen in HCl. Is equal to the molarity of the base times the volume of the base times the number of OH minuses in the base. And there's two OH
Well, that's pretty cool.
minuses in the base. Yeah, so this is sometimes referred to as the acid-base titration equation. The only disadvantage to this equation is that it only works for acids and bases. Now it could be acid-base neutralization reactions. Now it could be modified to work for other types of reactions, but at that point you're starting to, you're starting to, potentially bite off more than you can chew, unless you have some serious, understanding behind it with the math and the mathematical chops to boot. So
Yeah, and normally when we like the students to do such problems, we the general way to do it, the general way we encourage them to do it is to use this
yeah,
dimensional analysis.
yeah, and this way is this is more universal. Like this will work every time. So like even
Yes.
for example, in a case like B, I do have acid and I do have a base. And so it is acid-base neutralization. But I could not use the titration equation here because the base is in the form of a solid. It's not actually a solution. And therefore the molarity and the volume wouldn't actually work. Does that make sense?
Yeah, that makes a lot of sense, actually.
Okay. Cool. Well, I have to, unfortunately, I would have loved to have gone over a few more problems with you, but it looks like we have run out of time. But I hope that this was helpful. And I will definitely be posting the full answer key to this, as well as the video of this session. I just have to do a little editing work, but hopefully I can get that posted tomorrow. And as always, thank you so much for coming to this session, and we hope to see you after spring break. Have a great spring break, and we'll catch you next time.